All right, folks, as I said, we'll go through some of these circuit problems. If you have particular questions, we'll certainly work on them. But somebody had asked for me to work a few problems, so I'm going to do them first, okay? The first one they want to look at was number 4. The voltage across the 2 microfarad capacitor. So in order to do this, the first thing you need to do is to find the equivalent capacitance, or at least the equivalent capacitance of these 2 capacitors, the 2 and the 4. These are what? Series parallel? They're in parallel, so I'll do the equivalent of that. 2 plus 4 is 6. And then that's going to give me a circuit that will look like this. 12 volts, 6 microfarads, 6 microfarads. And so the voltage across the 2 or rather the voltage across this top 6 microfarad is going to be 6 volts and 6 volts, right? Because they're in series and they split up that voltage evenly. Yeah.
So you do the parallel ones first, not the series?
In this case, you have to do the parallel first because this parallel portion is in series with that capacitor. Because there's not really a series that you could do, right? Like these two capacitors, they're not in series. Right? You see that? They can't be in series because there's a junction right here.
So if, say, like, there was one right on top of, like, the C2, like, before that junction, then that would be in series, but because there's the junction...
If there was a circuit, if there was a capacitor there,
yeah,
you could find the equivalent of these 2 capacitors first. But then you would have to later find the equivalent of what you found here with what you have up here. You follow what I'm saying? What happened? That if there was a 4th capacitor, you would still approach it the same way, but it wouldn't be incorrect to find the equivalent of these 2 capacitors. But then you would have to find the equivalent of these 2 capacitors and then add that to what you found down here. So it would just add an extra step. Sam?
Can you go ahead and show how you find the charge of everything too?
Uh-huh. Yeah. So I have my 6 microfarad here, 6 microfarad here. I find that they have 6 volts. Do you want me to find the charge on each of those individual capacitors? So the way I'd do that is I would find the overall equivalent capacitance. It's going to be 1 over 6 plus 1 over 6. 3, right? 2, 6, 1/3. Yeah, it's going to be 3. And so this equivalent capacitance is 3 microfarads. That's for the whole circuit. With 12 volts, it's going to be then the charge on this capacitor, Q is equal to C times V, is going to be 36 microcoulombs. That means that there's going to be 36 microcoulombs on this capacitor, and, not farads, coulombs, and 36 microcoulombs on this capacitor. And then once you get that, you can find the voltage. Like I could step back from that and find the voltage. The voltage is equal to Q divided by C, which is 36 microcoulombs divided by 6 microfarads. This divided by this is equal to 6 volts. So that's another way to get to the voltage, but it's kind of a circuitous way to get to it when it's a lot easier to say, well, these are the same capacitors. I just go split it up evenly. But it's you need to know how to do that, to find the charge and then step back and find the voltage, because some of your problems on your test, you'll have to do that. You won't be able to just say, oh, I can just split this evenly. Is that what you were asking?
Yeah,
You need to know how to do that, so it's a good question, okay? So let's see, so back to this question. What was I looking for? The voltage across the 2 microfarad capacitor? Well, look, if I know that this voltage is 6 volts, and this capacitor right here is the equivalent of these 2, then I know that capacitors in parallel, they have the same voltage, and they have the same voltage as their equivalent capacitance. So this one is 6 volts, and this one is 6 volts. They have the same voltage as the voltage across the equivalent capacitor. All right? So the answer is B. Yeah, Lathan?
Can you like explain like the capacitors being like parallel? Because I thought like the symbols had to be like directly underneath each other parallel. So like see how it is in the most left?
Oh, yes. No, I can have that. That's not important. What's important is the junction. That I have these two capacitors that sit between these two junctions. So really the junctions is what you want to identify. It doesn't matter how they're situated. In fact, like we did before, like in the OpenStack assignment, you can have circuits that look really funky. Like I could have, a circuit that looks like this, and then I could have it like this, and those are still in parallel. Right. It's really just the junctions, because notice here, I still got two capacitors sitting between two different junctions. When you start a junction, that opens your parallel branch, and then you find where it closes. And then however many paths, I have one path, two paths. So I have two branches on that parallel circuit. Just hang with me, okay? I know it's difficult because it's new, and you're sort of trying to fit all these different pieces together. But keep at it, all right? Let's do another one. Is that okay? May I move on to the next one? All right, even if you don't have this one completely, that's okay. Let's go to 11. Okay, so with these, we did one of these in class, or a couple, I think. There are several steps that you need to take. The first step that you need to take is ask, how is the capacitance affected? C is equal to epsilon naught A over D. And what I'm doing here, I doubled the area. So if I double that, I double this, because it's a direct relationship. So my capacitor has doubled in capacitance. It has twice the capacitance. The second thing that you need to do is ask, what is constant? And you're really only going to have two scenarios with these types of questions. Either the charge is going to be constant. That's where you charge it up on a battery, and then you pull it off the battery. In that case, the charge is constant, because whatever charge you put onto that capacitor, that's what you got. So either the charge or the voltage. And the voltage is constant if you're leaving it hooked up to the battery. In this one, we're still connected to the battery, or the batter in this case, so the voltage is constant. Okay, and then the third step is you go Q is equal to C times V, and then I say, well, my voltage is constant. I want to know the charge, and so I've doubled the capacitance, so I double the charge. So whereas it was Q, now it's going to be 2Q. So,
So what, like, instead of the voltage being the same, like, what would be a scenario that the charge would be the same?
So the charge is the same. I think we did one of these in class. The charge would be constant if you charge up the capacitor and then you disconnect from the battery. Okay, yeah. So like number 5. Because when you hook your capacitor up to the battery, you put charges on that capacitor. Just like the guy with the little boost pack that he put in his car, like he put charges on that, and then he stops putting charges on it. And then you have a capacitor there with charge on it. And no matter what you do to the capacitor, those number of charges isn't going to change. Okay, but in that case, when you change the capacitance, you don't change the charge because that stays constant. You change the voltage across the capacitor. Okay?
And that would be like an inverse relationship.
Right. So if the charge is constant, if you change the capacitance, whatever you do to the capacitor, the voltage will do the opposite. All right, 13 was next. Here, what is the charge on the 6 microfarad capacitor? What do I know about charge on capacitors in series? Capacitors in series have the same what? Voltage or charge? Charge, right. So what I have to do here is to find the equivalent capacitance, and then whatever that equivalent capacitance is, it's going to be this, the charge on the equivalent capacitance will be the same for all four of these capacitors. So on this one, I first find the equivalent, 1 over 3 plus 1 over 6 plus 1 over 12 plus 1 over 24. This is not a nice even number, so I'm going to use my calculator. I know I was doing it with a student earlier. This is 1.6 microfarads. So that is the equivalent capacitance. And Q is equal to CV. I have 1.6 microfarads and 18 volts. And so I get 28.8 or 29 microcoulombs. So the charge that I have on the equivalent is 29 microcoulombs. And then I also have 29 microcoulombs on this one, 29 microcoulombs on this one, and then the same for those other two. Because capacitors in series have the same charge. Then if you wanted to know the voltage, then you could go along and you say, well, V is Q divided by C. So I'd say 29 divided by 3, 29 divided by 6, 29 divided by 12 to get the voltages. And those voltages better add up to equal to 18 volts. Yay? Okay. All right, you'll probably have one. Oh, here's another one. So, well, this is the same circuit, isn't it? Okay, so if I want to know the potential across the 6 microfarad capacitor, isn't this exactly the same? Yeah, so I know that I have 29 microcoulombs there. So if I want to know this voltage, it's Q divided by C. That's 29 divided by 12, so that's 2 point something. Huh? Oh, okay. 29 divided by 6, so it's 4.8. And then the last one here, and then we'll open up the all questions, is 50. The last one. Oh, no, not the last one. Two capacitors are connected to a voltage source. How does the total charge stored in a series combination compare to the charge stored in a parallel combination? What do you think is going to hold more charge? Your series or your parallel? Why? You're right, but why? Who said that? Was that you, Allie? Why do you think that? Yeah, you're correct in saying that, but that's not really the reason. The reason is that the in parallel, your capacitors will have a higher voltage because they don't share the voltage, right? They each have the same voltage. So if you had two, so the answer here is a parallel would hold more charge. That if I have two capacitors here, if I say this is 12 volts, this will be 6 volts and 6 volts. And say these are 2 microcoulombs or microfarads, 2 microfarads. Then I'll have 12 microcoulombs on each of those. But if I have them in parallel, then I would have 6 in this case I'd have 12 volts and 12 volts, so I'd have 72 microcoulombs on each, right? 6 times 12, or excuse me, 24 microcoulombs. I'd have 24 microcoulombs, 24 microcoulombs on each of those. Okay? Y'all with me on that? I know this is fast, and I know that it's going past some of you, and I think I'm okay with that. I think that the more practice that you do, the better you'll be off. Okay? All right, what else? Do y'all have particular ones that you want to look through, or do you just want to start at the beginning? Does anybody have any particular ones they want to look at? Okay. Well, let's start with this one. What is the equivalent capacitance of this circuit? Let's just take a step back. All right. Look at it. I know I got I know I got some parallel circuits. I usually start on the big side, so I come this direction, okay, because my big side is here. I know coming right here that I have a parallel branch opening up. And then I look to see how many parallel branches. Now, this one is sort of written like we usually do it, so I can probably look and see that there are 3 parallel branches. But if it's not obvious, count count your junctions, see how many branches you have, and you can identify a new branch by following it until you come to a capacitor. So here's 1, here's 2, here's 3 branches. I have 3 distinct branches. Notice I just followed them until I came to a new capacitor. And that identified my 3 different parallel branches. And then also notice that up here I have 2 capacitors that are not in parallel. There's no junction between these 2 capacitors. And so that tells me I need to start up here, and then I'll add these to those. 3 and a 6 in series. That's 1 over 3 plus 1 over 6. That's equal to 2 microfarads. So these 2 capacitors are equivalent to 2. And then so what is the total equivalent? 5 is right. 2 plus 1 plus 2 is 5. Now you'll have one like that where I ask you, but then I'll also ask you what is the voltage across one of those. Can y'all tell me what the voltage is across the 6 microfarad capacitor? I don't remember, it's 4. Across big capacitors, you get small voltages. It's an inverse. All right? Be careful with that. Students will get confused about that. And in fact, when we do resistors, you'll find that the opposite is true. Across big resistors, you have a big voltage. But that's okay, because y'all are shocked.
Wait, so what did you say, the voltage of what?
The voltage across a big capacitor is small. The voltage across a small capacitor is big. It comes about because of that Q equals CV. Q is constant. If C is big, V is small. It's an inverse relationship. Okay? But if you want to go about it the harder way, then we know that the equivalent of these 2 is 2 microfarads, and that they have 12 volts across them. And so the charge on each of them is 24 microcoulombs. 24 microcoulombs. Right? C times V, 2 microfarads times 12 volts is 24. And then since they're in series, they all have the same charge. So I got 24 and 24. And then if I want to find the voltage is Q divided by C, 24 divided by 2. Oh, I'm sorry, 24 divided by 3 would be 8. 24 divided by 6 would be 4. So I forgot what the question was. What are we looking for? No, that was this one. Across the 6 microfarad, what did I say it is? It's 4 volts, right. Okay, 24 comes about because these 2 capacitors up here, they have an equivalent that is 2 microfarads. Okay? And I know that 2 microfarad capacitor, it's like it's hooked up to its own 12 volt battery. That there are 12 volts across that 2 microfarad capacitor. And so that's where my 24 comes from. 24 microcoulombs, because charge, Q, is equal to the capacitance times the voltage. Q equals CV. So if I want to know the charge on this capacitor, I say 2 times 12, C times V is equal to 24. But capacitors in series have the same charge. So this 24 microcoulombs is also on this one and on this one. Capacitors in series have the same charge. They have the same charge as the capacitors, as the equivalent capacitor. All right? Let's do another one. Let's find one that's a little bit different. Ooh, I like number 8. Don't y'all like number 8? I like it because it makes you think about it more deeply when there are no numbers. So here I have capacitors, 3 of them, and I just want to know the voltage across C1. Now, notice that these two are in parallel. So if I were to draw an equivalent circuit, it would look like this. This one would be C, or C1. They're all the same, so I'll just call them C. What would be the capacitance of that second one? 2C. And I got 12 volts down here. What's the voltage across this capacitor, which is the same as this capacitor? Well, I don't know. Do y'all know? Do you have any guesses? Or not guesses, but who said that? You're right. It's 8. All right, this is no different than what we did before, where we said if this was 3 microfarads and this was 6 microfarads, right, that this one is half this one. And if you have a capacitor that's half the other, you know that its voltage has to be twice the other because it's inverse. And so I also know they have to add up equal to 12. So I have 8 volts, and then this one's going to be what? 4 volts, right. So you can't, I guess you could put in numbers for C, like you could say C is equal to 1, and you'd have a 1 and a 2 microfarad. But you can't figure out the charge. You really have to think about how the voltages are distributed here, just based on the differences in the capacitors. Let's do this one. What is the equivalent capacitance of this arrangement? Where would I start on this one, on number 9? C1 and 2. Right. Let's just follow the circuit through. I come here. No branches yet, no parallel yet. But when I get here, I see that I do have a parallel circuit. I have a parallel circuit that has 2 branches in it. I know that it's 2 because I follow to the first capacitor, that's 1. And then I follow this to the next capacitor, that's 2 branches. And then as I follow the second branch, I see that I have 2 capacitors that are in series. There are no branches in between, no junctions in between these 2 capacitors. And then they come back to where this junction closes. And so I want to start with the smallest portion that's either series or parallel. And so I'll start with this portion. A 4 and a 4 in series, 1 over a quarter plus a quarter, it's 1 over a half, is 2 microfarads. And then, what do I do next? The parallel, right. I got a 2 and a 4 in parallel. This big thing right here, 2 and 4, this big thing is going to become 6 microfarads. And then I just have 2 6 microfarad capacitors. Six and 6 microfarads over 12 volts. Oh, I want to know the equivalent. To find the equivalent of that, 1 over 6 plus 1 over 6. That's 1 over a third. That's 3. So 3 is the right answer. Valerie?
How is C4, I know it's a stupid question, but how is C4 not parallel with C3 and the other two? Because it's like separated by junctions.
I know. That's a good question. The reason is because before I get to C4, there's no junctions. Right? You see any junctions right here? My junctions don't come until after C4. Okay? And so that's how I know that this thing sits in series with this thing. That there's only a single path to get to C4. That's hard to see, isn't it? It's difficult to look at these circuits and see what's in series or parallel. Like you might even say, well, gosh, why aren't these in series? These look like they're in series, but look, there's a junction that breaks off. And so they're not in series because I have this junction that breaks off. Okay? But once you get the hang of it, after a lot of practice, it'll be easy. Like it's really not that complicated. It's just there are a lot of little pieces that have to fit together, and that's what makes it complicated. It's like driving a car, right? Driving a car is not that hard, is it? Every little individual piece is not that hard. But like my 9-year-old, she can't drive a car. All right. Okay. So what are we doing? Oh, can we say the voltages? What's the voltage? So the equivalent is 3. What's the voltage here? Yeah. The voltage on this capacitor. Let me ask you another question. What's the voltage on this capacitor? 6 volts. I know it's 6 volts because this is 12 volts. And these two are identical, so they split it up evenly. So I got 6 volts here. What do I have here? 6 volts there. What is the voltage on this capacitor? Careful. 6. So this capacitor right here is the equivalent of this capacitor. And so the voltage across this capacitor is the same as this one. Let me write that down. So this capacitor has 6 volts. It's the equivalent of these 3 capacitors all together. And so I've got 6 volts on this one because capacitors in parallel have the same voltage, and they have the same voltage as their equivalent capacitor. And then also, across these 2 capacitors, I also have 6 volts. So what's the voltage across C1? 3 volts. And C2? 3 volts. Okay? I have a
Voltage, C4. You can write it out.
C4? Yeah, okay. So back at the first step. I know I have 12 volts here, and I have 2 identical capacitors in series. I know that for capacitors in series that V1 plus V2 has to equal the total, and only because these are the same capacitor, I know they have the same voltage. And the only number plus itself that's equal to 12 is 6. Okay? Yeah, y'all stop me if you're confused, Britt.
In parallel, they have the same charge. It's a voltage. Series, they have the same.
Right. Capacitors in series have the same charge. And they have the same charge as their equivalent capacitor. Capacitors in parallel, as you said, have the same voltage. And they have the same voltage as their equivalent capacitor. When I say they have the same voltage, that's what I mean. That they have the same as their equivalent. Do another one. Look, see, there was number 10. There was a question, what's the voltage across C1? And it's 3 volts. So I would very much expect that you have a question where it asks you, what's the equivalent? And then another question that asks you some follow-up. What's the voltage or the charge? And then maybe even another question that asks you a follow-up. Okay? Although I try not to have too many series of questions, but you might see that. Oh, where's that one I wanted to show you all? We'll come back to that. Oh, number 19. So number 19, this is sort of like your OpenStacks too, where you have this circuit, and we want to figure out what the heck is going on. I come along here, and I come to a place where the wire splits into pieces, and I want to figure out how many pieces it splits into. As I come into this circuit right here, I follow it along. I follow it there until I come to a capacitor. That's 1. I follow it there until I come to a capacitor. That's 2. And then I follow it there. That's 3 different branches. So I have 3 branches in that parallel circuit. And then I come along here, here, and then here. It ends right there. It sort of looks funky, right? Because you have that diagonal branch. But it's really no different than what we've drawn before. This is the same circuit. All right, so if I want to know the charge on C2, what's the voltage on C2? 12 volts. And since it has 12 volts and 2 microfarads, then the charge is 24. C times V, 2 times 12. Y'all know number 15? See if you can do 15 without just look at it and see if you know what 15 is. Who knows what it is? What is it? It's 1, right? I have a 1 and a 1 in parallel right here. 1 plus 1 equals 2 microfarads. And then I have a 2 and 2 in series. 1 over 2 plus 1 over 2 is equal to 1. Y'all get that? Yeah? Good. And then if I want to know the voltage across C3, you know what that is? That's a little bit harder, but not much. I have a 2 and a 2 in series. What's the voltages on those two capacitors? 6 and 6, right. And so what's my voltage here? 6. And here? Because capacitors in parallel have the same voltage, and they have the same voltage as their equivalent capacitor. So if I have an equivalent circuit, it looks like this, that is 2 microfarads and 2 microfarads. This is 12 volts. I'm going to have 6 volts here and 6 volts here. And whatever I have on this capacitor, which is the equivalent of those two in parallel, that voltage will be across both of those capacitors. Yeah.
Why do you get the parallel capacitance before the series? That's just what you always do?
No, not always. You want to take the smallest part. She asked, why do you take, in this problem, the parallel capacitance before the series? Often that's the case, but not always. I'll show you one where it's not the case. You want to take a part that is only series or only parallel. This thing has no series capacitors in it, and so that's why I choose it. So I take this first because there's nothing in series here. And then once I find that, I combine it with what it is in series with. Because this comes in series with this capacitor.
So if you would have done like C1 and C2 first, you would have had.
No, you can't do C1
No,
and
you
C2.
can't. But like that's what you can't do because C2 is like parallel and in series.
Right, it's wrapped up. C2 is wrapped up with C3. It's already part of a parallel branch. Let's see, there's one, I'm certain there's one where you have to do series first. Like number 15, or number 12 rather. If you want to know the equivalent capacitance of that, where are you going to start? Oh, and by the way, yeah, you're right. But by the way, on this, it looks a little bit different because there's no power supply. But if it helps you, you know, just draw your power supply like that, and it's the same circuit. So here, you would start with 15 and 3. Then you would combine that with the 6. Then you would combine that with the 20. Let's do the 15 and 3 first. It's going to be 1 over 15 plus 1 over 3. Oh, is this even? Are these even numbers? 2.5? Exactly. And then I combine that with 6. That's going to be 2.5 plus 6. I can do that. That's 8.5 microfarads. And then I combine it with the 20. But it's A, right? It's the answer A. I do 1 over 20 plus 1 over 8.5. That's 6. It has to be 6. You know why it has to be 6? Because when you have capacitors in series, this is a neat little trick. It'll help you with resistors too. When you have capacitors in series, the equivalent capacitance is smaller than the smallest capacitor. We talked about this early on. That imagine you have two bowls, one's big and one's small. And remember your capacitors are linked so that they have the same charge. You're going to be limited by the smallest bowl, right? If they each have to have the same amount of electrons in them, you can't have the big bowl full because then the small bowl will be all overflowing. You follow what I'm saying? You're limited by the smaller container. And in fact, you're even more than limited when you have two or more capacitors in series, that you actually have a value that's less than the smallest capacitor. So all that to say that the equivalent I have a 20 and an 8.5, the capacitance has to be less than 8.5. So that gets rid of B, C, and D. It only leaves A. Okay? That's a handy little trick. It will help you on some problems. You don't have to know that because you could just do this. But if you knew that, you could just, move right along and say it's 6 and not worry about it. Okay. It's helpful for you? Practice, practice, practice. That's what helps. In fact, if you printed these out, go back and work the ones that we didn't do. And the answers are in the back. Just want to point out that there are some common numbers that I like to use. We've seen the 3 and the 6, the 2 and the 2, the 3, 3, and the 3. That works out well because it's a third plus a third plus a third. And that's equal to 1. What's something else I like to do? What's that? What do I like to do? Yeah, I did the 2 and 2, but there's another pair of triplet that I like to do. 3 over 8. What was that? So that would be 8. Oh. Does this work out? That would be 8 24ths plus 3 24ths. Yeah. So something like that would be equal to 2. You follow what I'm saying? So look for those. There are some combinations of numbers that'll give you even values for your capacitance. But on the test, it won't necessarily be even. So you'll probably have 1 or 2 that are decimal numbers. But I try to make the math as easy as possible. Okay? Of course. Well, let's just put some numbers in. Is that okay? Let's say that we have a 2 and 2 in series and a 2 and 2 in parallel. The 2 and 2, 2 and 2. I know this right off is 4 microfarads, right? 2 plus 2 is 4. And I know that this is 1 over 2 plus 1 over 2. So that's equal to 1. So what's the answer then? The equivalent capacitance of the series, this value, is what relation to this value? 1/4 D. That's probably the easiest way. There are some other ways you could look at where you actually just keep the variable C, but I think that's the easiest way. Just put values in. Any others you want to specifically look at? Okay. Let's see here. What's some harder ones? Yeah. Yeah, you'll have energy problems, but I would expect them to be fairly straightforward. They might be wrapped up with a circuit where you have to find the voltage and then find the energy. But here, if I wanted to find the energy in C1, I have Q and C right here. Remember, my energy is 1/2 CV squared. I don't have VF, Q, and C. There is an alternate expression. Gosh, what is it? Is it Q squared over C or Q over C? I always forget. Do y'all know? Do you know what it is? I can't remember. Let's see. I think it's Q squared over C. Is that right? I would have to do a V. It's a substitution, right? Yeah, that's right. That's right. Q squared over C. So you could do that where you say this is equal to 1/2. Those are on your equation sheet. Q is 100. A pico is 10 to the minus 12. And then you square that. And then C is 10 times 10 to the minus 12. be careful your 10 to the minus 12s don't cancel out. So I have 100, so 10 to the minus 12 squared. I get 5 times 10 to the minus 10. You could, yeah, you could cancel out. But it's going to be a little tricky because you'd have to cancel this out and then just cancel one of these out. In your calculator, it's probably just easier to leave them. Okay?
Question about conversions.
Yeah.
So long. This class,
Sure.
I forgot, like, when you're doing the length times the area stuff, and you have to convert, like, centimeters squared to, like, meters.
Uh-huh.
Squared.
Okay.
You square it again.
Yeah. Probably useful for everybody to see that. So, first of all, if you're, say, converting microcoulombs to coulombs, right? Then in order to do that, say I have 2 microcoulombs, I would say, well, 1 microcoulomb is 10 to the minus 6 coulombs. And that's how I convert that. Cancel these out, and I'm left with coulombs. 2 times 10 to the minus 6. But say I'm instead converting centimeter squared to meter squared, which you had to do on your OpenStax assignment, or you have to do it for tonight. In order to do that, let's say I have a 100 or 1,000 square centimeters. We'll say 10,000 square centimeters. Because I know that that's a square meter, right? Because 10,000 square centimeters, that's 100 times 100 centimeters. So it's going to be a square meter. Then I have 1 meter is 100 centimeters. But I have to square that conversion factor. And that's equal to 1 square meter. So yeah, if you're converting squared units, you have to square the conversion factor. On the test, honestly, I'm not gonna make you do that. You should know how to do that.
Yeah, maybe that's what you do. It's so long since I've been doing this stuff.
Okay.
Sometimes I gotta refresh.
Yeah, it's important for you to know how to do, but I consider that something you've already mastered. Okay. It does come up on the OpenStax. Any others stand out to y'all? About 5 or 10 more minutes. Are y'all brain dead? Yeah, you want to stop there? Or another? You tell me. It's good time. Oh, what about this one? It looks different, doesn't it? But don't be afraid of it. Like it's, I do it just like the others. I come along, I look for my first junction. This is my first junction, and it splits into 2 pieces, and then it closes right here. And then I have another junction, and it splits into 2 pieces. So what I have here are 2 parallel branches that are in series with one another. So I'd find this capacitance, and then I'd find this capacitance. What is this one? 6, and this one is 12. And so I have a 6 and a 12 microfarad in series with one another. 6 microfarads, 12 microfarads, and then 6 and 12, what is that? 1 over 6 plus 1 over 12. That's equal to 4. Good. So B is the right answer. Look at this one. This one's a little bit different. But in this one, I have a parallel branch, but notice that it has 2 series within it. So I'd have to find the series before I would find a 1 over 2 plus 1 over 4. That's 4/3. Right? Yeah, 4/3. And then I have 2 of those in parallel, so I'd say 4/3 plus 4/3, which is 8/6. Oh. Yes, 8/3. Thank you. Sorry. So the equivalent of this would be 8/3 microfarads. Okay? You know what the voltage across the 4 microfarad capacitor is? Well, I know I got 24 volts across this because it's in parallel with this. So I also have 24 volts here. Y'all see that? I have 24 volts here and 24 volts here. Let me redraw it. Maybe you'll see it. Draw it in a way that we've seen. These are the same circuits. I have 4 and 2 microfarads, 2 and 4 microfarads. Those are the same circuits. I just flipped it on the side and sort of finagled with these wires up here. These are exactly the same. So I have 24 volts across this. And I know that that 4 and 2, they're going to split up that 24 volts. The 4 microfarad capacitor, big or small voltage? Small. It has to be half the voltage across the 2. So I'm going to have a small voltage plus a big voltage that will add up to 24. What's that going to be? 8 is the right answer, okay? Because I have 8 volts here and 16 volts here, which add up to equal to 24. Need lots and lots of practice, okay? I know that some of y'all are still not quite there, and actually all of you are not quite ready for the test. So take the rest of these problems and work through them. Come see me if you need additional help. We're going to see resistors, and I hope you saw them because they're similar, but they're also a little bit different.